Hi, welcome to our webinar, Overcoming the Challenges of Detecting P2P Botnets on Your Network. I'm your host, Chris Grove, Technology Evangelist here at Nozomi Networks. Joining us today is Ivan Speciali, Security Researcher, and Giannis Saraias, Cyber Threat Analyst from our Threat Research Team within Nozomi Networks Labs. The security research team works daily on lots of different activities, but the most important mission is to keep our customers safe by providing indicators, signatures, and detection tactics delivered using our threat intelligence service. The team also publishes our cutting-edge research to the community by releasing white papers, advisories, or contributing to cybersecurity conferences. So you may have seen them before, but regardless. Ivan and Giannis, would you please introduce yourself?
Hello, everybody. My name is Ivan, and I'm a security researcher at Nozomi.
Hello, I'm Giannis Saraias, and I work at Nozomi Networks as a threat analyst.
So today we're here to discuss some of their observations from an interesting component in the attacker's tool chest, the emerging technologies of botnets, and more specifically, P2P or peer-to-peer botnets, such as Mozilla, DDG, FritzFrog, and others. These botnets allow attackers to carry out large-scale malicious operations. So we have an exciting session planned for you. But as a reminder, we'd like to ask you to go ahead and ask us some questions for our Q&A session at the end. You can see that in the questions window of the GoToWebinar. So without further ado, let's begin. Ivan, can you introduce botnets in general and tell us a little bit more about what we'll be diving into today?
Yes, thank you, Chris. First, it might be obvious to most of the attendees today, but I'd like to clarify first what we mean by botnet. By botnet, we intend a collection of machine or devices infected by the same malware, which is managed by a single entity, which we call the botnet operator. Different machines might have a different version of the protocols. Think about the updates, for instance. But as long as they talk the same network protocol with the controlling identity, they logically belong to the same botnet. It's obvious that in terms of resilience, the link between the controlling entity and the infected machine has always been the weakest point in a botnet. And during time, it was the subject of a pretty interesting evolution that you're going to see in part today. So the first botnet were following a pretty basic client-server mode, typically using simple protocols like IRC to receive commands from the controlling entity, or plain HTTP. This centralized approach is pretty straightforward to implement, and while it can be effective to protect the botnet from hostile takeovers from competing botnets, it's not very resilient when legal authorities came into play. For instance, once a server that is functioning as a controlling entity is identified, a legal authority can give access to the server to a government agency or to a private company, which is tasked to take down the operation, and all of a sudden, the botnet is shut down. So it's pretty clear that in terms of resilience, this model wasn't just enough for botnet developers, and soon there were the first experiments with the peer-to-peer architectures. Peer-to-peer architectures are pretty compelling in the sense that they lack central point of failures, which means that there isn't a single server that can be taken down and taking down the whole botnet operation together with it. But at the same time, the botnet operators need to establish a mechanism such that the single participants of the network are able to identify the command sent by the proper botnet operator and not by somebody else. And this is typically achieved through public cryptography, which means that the bots, within their code, they embed the public part of the public key pair, while the botnet operator, the controlling entity, as the private key, which is used to sign the commands that are then distributed to the network. The pure peer-to-peer implementation, while it's pretty nice or resilient, has some drawbacks, which, for instance, can be in terms of speed. Think about when you're trying to bootstrap your a torrent that you are downloading. It takes some time to actually find all the peers that you would use to download the file from. And this is where hybrid peer-to-peer botnets came into play. In this configuration, we have some servers that act as a privileged roles, have a privileged role, which are typically called super nodes. And for instance, depending on the design choices of the botnet developers, they're used to bootstrap the communication. For instance, once a new machine is infected, it can contact one of these super nodes to fetch the list of the, let's say, the 100 most fastest peers. Obviously, the botnet will be able to survive a takedown of one of these hosts and will be able to promote another server to this role. And this is a pretty, let's say, interesting evolution. Together with these architectural changes over time, a large array of tricks, techniques emerged that have been tested and have been proven successful. And in no particular order, the first is, for instance, bulletproof hosting, which means finding some interesting provider, let's say, that is willing to turn a blind eye on your malicious activities if you're a botnet operators. This approach did work for a while, but as soon as security researchers started to cooperate and sharing this IP and then identify subnets and then identify autonomous system, this approach didn't scale because any activity coming from these dodgy providers immediately got flagged, independently of whether they were actually good or bad. Another interesting technique that came out with time was fast flux, a basic version of which consisted in changing very frequently the mapping between a DNS name and IP address. And this allowed a botnet operator to switch frequently the actual machine serving, for instance, new malware. Another very interesting technique that is pretty heavily used even today is a DGA, or domain generating algorithm, which consists in embedding within the bot an algorithm that is capable of generating domain names, typically over time, which means that if we run the algorithm today, we will get a specific domain name. If we run the same algorithm tomorrow, we will get a different domain name. This is used, for instance, when a botnet is not capable of reaching the configured center of command and control as a fail-safe mechanism. So all what a botnet operator has to do to get the control back of the botnet is registering one of these domain names. And since he owns the private key, he will be able to forge new commands for the botnet. This technique, as I said, is very used still today. And one example of how to take down a botnet that is using this technique was employed by Microsoft early these years to take down a botnet called Neighbors. The approach taken by Microsoft consisted in generating 6 million different domain names that were covering a period of time of 25 months. And by sharing this very big list with all the registries involved, they were able essentially to provide a blacklist. So whenever the botnet operators were going to turn to this registry to register one of these domain names, they couldn't. So the idea here is that since this operation is still taking place, 25 months is a period of time long enough to clean all the machines involved. And it also buys the time, which allows you to generate even a further list if you need more time. A last technique that I really like to talk about is the blockchain-based naming protocol. The idea here is that rather than relying on DNS to change the mapping between an IP address and a domain name, since domain name, as we saw in the case of DGA, requires a registry, an interaction with somebody that might allow or not allow you to register a specific name. With blockchain-based naming protocols, you essentially use a blockchain like the Bitcoin one, which is permissionless. And you just need to do some transactions on the blockchain, which can actually guarantee you a level of anonymity. Next slide, please.
So, Ivan, I think it's important to note there that if somebody looks at all those capabilities that these botnet operators have put into their enterprise, it's more security than some of their targets have. Some of their targets only wish that they were able to take advantage of some of these technologies to secure their environment, and these guys are using them on the attacker side. So they're very sophisticated with the different tactics that they've introduced.
Absolutely. By several means, these operations are pretty serious. Sometimes when you read in the news about botnet operation or another, it's, let's say, by the first look of it, it can be complicated to understand whether it's something sophisticated or not. But let's say, for instance, the size is a good indicator, although it's not consistent over time. The use of some exploits, it could be, but again, it depends on a case by case. So we saw the case of Microsoft where and makers, which took a lot of effort, both from a technical point of view and also from a organizational, to take down a botnet. But our task, what we want to achieve right now, is something which has more impact for ourselves and doesn't take this effort. And this is essentially looking at our network. So let's say you're tasked with defending a specific network as big as you want. A good approach to understand whether you actually have some peer-to-peer botnets within your network, and in that case eradicate those, is to look at 3 different phases that these threats actually use. The first one is the bot deployment within a network, which means that you're running your network and some external actor is trying to install its bot within your network. The second phase is the peer-to-peer communication. So one of your assets got infected and it needs to establish a communication with the rest of the botnet. So this is the second phase. And then we have the third phase, which is where the malicious activity takes place, which can be either mining from cryptocurrencies or sending spam, performing DDoS, and even enrolling other hosts from other networks into the botnet. And it's now the moment to try to see the first botnet of the day with Giannis.
All right, thanks for the overview, Ivan. So one of the botnets that we looked at is called DDG. It has been around since late 2016 and it's still active to this day. So its main goal is to infect servers and use them to mine the Monero cryptocurrency. So it mainly spreads by guessing SSH credentials and exploiting some vulnerable services like OrientDB and Redis. So the choice of Monero as a cryptocurrency is quite interesting because it's one of those cryptocurrencies where mining with a general purpose computer is quite profitable, especially in the case of a botnet where you have access to possibly thousands of computers and you don't have to pay for the electricity powering them. So if we look at DDG using the model that Ivan described with the 3 steps, during the deployment step, what we would notice is DDG scanning the IPv4 address space to find SSH servers, then trying to guess their credentials in order to get inside, or possibly exploiting one of the services if it happens to be vulnerable to the exploits that it includes. So, I mean, scanning the IPv4 space, theoretically you can do that in a few hours if you have a fast enough connection. Once the attacker is inside the server that they have targeted, they will join the rest of the bot network. They will set up a crypto miner, botnet persistence, and then the actual malicious activity will begin. So in the case of DDG, the main malicious activity that it is performing is to mine the cryptocurrency, and occasionally scanning the internet for more hosts in order to expand the botnet. An interesting thing that we noticed was that some of the earlier versions of DDG, the command and control was mostly based on a centralized form. So it would include the list of IPs and domains that were hard-coded inside the samples. But now it's using something a little bit more sophisticated. What it's using now is a custom hybrid peer-to-peer based protocol, we could say. So it still includes those IPs and domains inside the samples, and it will try to communicate with each one of them. But the idea now is that even if those are taken down eventually, as long as it has set up a peer-to-peer network, it can continue communicating between different peers. So in that case, the moment that an infected server joins the network, it's going to talk to the supernode, retrieve a list of infected peers, and then they can interact to share configuration files, binaries to execute, and so on. Another interesting thing about DDG is that it is showing awareness of competitors. What that means is that as soon as a server is accessed, it will check if certain processes are running, and those processes might be related to competitors that are using the same type of business model. So it will try to kill those processes, disable any services, even block domains that it knows are related to some of the competitors. And some of the traffic that DDG generates, it looks like HTTP, but some of the header combinations are quite unique. So we have added a snort rule in the blog post that you could look at in order to detect it. And I think now Ivan is going to talk about the FritzFrog botnet.
Yes, thank you, Janis. So FritzFrog is a relatively recent new peer-to-peer botnet discovered a few months ago by researchers at Core. The goal of FritzFrog is to mine Monero cryptocurrency and to enroll, of course, new machine into the botnet. The FritzFrog uses heavily SSH credential brute force. Another interesting peculiarity of FritzFrog is that it pipes all the commands between the peers through SSH. So FritzFrog is not groundbreaking per se, but it's still an interesting test case of our 3 phases model that we described earlier. So by applying this methodology, we have the bot deployment phase, and we will see, if we look at the actual logs into the servers, a spike of SSH connection attempts. If we instead see the same activity from the network point of view, we'll see a lot of again SSH session trying to establish a session, but actually failing. And let's say that one of these credential brute force completes with success, we will have a peer-to-peer communication, and this means that a new SSH connection will be established with an unknown host or many more hosts, and this will represent an anomaly. The third phase is the malicious activity 1, and in this phase we will have either new SSH connection attempts toward other hosts that we're trying to enroll within the botnet, and again this will definitely stand out because we will see new credential tried, so connection trying to be established, but most of those will fail, so a failure rate. And since, as we said, FritzFrog goal is to mine Monero, we will also see connection towards the Monero mining pools. So FritzFrog per se is quite noisy, as we've seen, and using SSH for peer-to-peer communication, while it does buy you confidentiality in a sense, it doesn't hide the network activity. And we can move to see Mozilla, which I think it's probably the most interesting botnet of the day with Janis.
All right, thanks, Ivan. So Mozilla is quite interesting, mainly because of the way the command and control communication works. Essentially, the traffic is hiding among what looks like legitimate traffic. So it's mainly targeting embedded devices, so that is things running on the ARM and MIPS architectures, So you can think of routers, digital video recorders, and web cameras, things like that. It includes a number of exploits, mostly for command injection vulnerabilities, but it also uses weak telnet credentials in order to propagate. So one thing that's worth mentioning at this point is that the different types of targets that are attacked by a botnet also determine the viable monetization strategies. So if you're attacking embedded devices, usually the specifications that they have are quite low. So using them to mine cryptocurrency is just not very practical. So what you do in this case is you can convert the bandwidth that you have access to into profit by offering distributed denial of service to any willing customers. So while the two botnets that we looked at earlier, DDG and FritzFrog, they both relied on mining Monero and they targeted actual servers. Mozilla is targeting embedded devices, so its main method of monetization seems to be DDoS. So its peer-to-peer protocol relies on, it's very similar to the DHT-based protocol used by BitTorrent. So that's a distributed hash table. So essentially, it's piggybacking on this existing protocol and its infrastructure to bootstrap its own network within, which is very, very interesting. For example, it might use router.bittorrent.com, which is something that you would use when performing a normal torrent download, and will use that to bootstrap itself. So to the casual observer, if you're not aware of the peculiarities of the protocol that Mozilla is using, it might just look like a normal BitTorrent interaction within a network. So regarding its capabilities after the infection, it can perform a large number of denial of service attacks, and of course download and execute any binaries that it is instructed to do. So, all right, so now let's look at this from the perspective that Ivan described, with the model with the 3 steps. So during the deployment phase, Mozilla is mostly going to be probing networks by port scanning them. Hopefully it will manage to find a telnet server. Then it will attempt to guess its username and password to get access. Additionally, it might use an exploit if it happens to find a vulnerable service that it has the ability to exploit. So at this point, the attacker has access. He starts communication with a DHT node. He gets a list of active peers. He begins communicating with them, transferring configuration files, and so on. Now, this step, it might be flagged as suspicious in a network, depending on the current network policy. That is, maybe BitTorrent traffic is just not the norm, so it's going to stick out. Or maybe it's just something that's quite common. So in this case, this command and control communication is not something that is going to be easy to notice. But after that, it's going to begin the malicious activity, which is quite noisy, looking at it from a network perspective. So it will try to expand. So again, we're going to see the port scanning of random IPs that we have never interacted with before. Telnet login attempts, many of them per second, very large number. Additionally, it will host Mozilla samples for other nodes that are joining. So essentially, it's going to pick a random TCP port, and it's going to run an HTTP server on that one, providing Mozilla samples. And of course, it can launch a denial of service attacks when it is instructed to do so. So while the interesting part about Mozilla is the command and control infrastructure that it uses, it's quite stealthy. What we notice is that after the infection, the actual attacks, the ways that they monetize this botnet, they're going to be very noisy. Port scanning, DDoS, and so on. So now Ivan is going to summarize some methods for blue teams to detect those activities in a network.
Yes, thank you, Janis. So to wrap it up, we've seen how botnets evolve from very simple client-server model to a more complicated peer-to-peer and hybrid peer-to-peer. The goal of this evolution of this shift has always been improving the resilience of the whole operation. This resilience in face of takedowns has definitely improved over time, but this, as we've seen, doesn't translate into a stealth operation. When you actually look at the network activity, there is a lot going on. So we've seen how it is pretty complex to dismantle a global complex peer-to-peer botnet like Networks. But when we zoom into a specific network, which could be the one we are tasked with manage, there's a lot that can be done to disrupt the operation within our network with the right tools and the right methodology. And I think we can take questions for now.
Yeah, very, very interesting, Giannis and Ivan. Thank you very much. So it looks like we have a couple questions to ask here. So first, from a defender's perspective, sorry, let me move my questions over to the screen here a second. Okay, from a defender's perspective, is it easier or more difficult to defend against P2P botnets compared to other command and control variants?
So obviously, it's more, it depends what you mean by defense. As we have seen, we have like 3 phases, and the peer-to-peer networks is definitely more powerful, even for the bot deployment phase, because, for instance, we can see different hosts targeting our network in order to expand there. For the communication, absolutely, because we don't just have one single IP, one domain name to blacklist, but peer-to-peer botnet can receive commands from potentially thousands of different hosts. So yeah, the idea is that it's definitely more complicated to defend against peer-to-peer botnet.
Yeah, that anomaly detection, I think, is going to be very helpful when it comes to detecting these types of activities. Yeah. So another question we have from Derek is, do you believe botnets are a unique risk for industrial control system environments, or will normal defense in depth architecture be sufficient protection? So do you think defense in depth is going to be a valid approach to defending against P2P botnets in an ICS environment?
Yeah, I think defense in depth is a bit of an umbrella terms. So if implemented correctly, it will definitely, for instance, if you, something very basic like applying the proper patches, if you can find those, for many systems, this is the reality. Or let's say if you do proper segmentation, which is something which is often overlooked, but works pretty well. So this, I think that defense in depth is definitely the starting point. And then there might be some occasion, some outliers that can even go past that. But I think defense in depth is a very big baseline, very important baseline that should implement, and then will definitely improve the posture of your environment.
Great. So the next question is, what methodology is the correct one to remove the point-to-point botnet from my network? So before you answer that, I wanted to just quick mention, a while ago, I was at a factory in China that had a bot infection, and I got there to deploy our cybersecurity monitoring for their industrial control system, and they weren't really concerned about that botnet when we brought it up to them. They knew that it was there. They had been unable to clean it for over a year, and they just accepted the fact that there were hundreds of nodes that were infected in the factory that they could never uninfect. They were only worried about whether or not it was going to affect the industrial control system. So they kind of shrugged it off as an IT problem. They had made an attempt to clean it up, and they couldn't, and they just sort of accepted it as a user of the network in a way. So do you have any recommendations for being able to correctly remove a P2P botnet?
I mean, the first step would be to identify it in the network. So just like we described, you might not be able to easily identify the peer-to-peer communication part, but you will definitely see some of the side effects of its activity. It's either going to be connecting to a mining pool, or it's going to be conducting denial of service attacks. That's definitely something that you will notice if you have the proper network visibility and so on.
Perfect. Okay, so we have another comment, which is if you were talking about the botnet Microsoft has taken down recently, that the botnet is back. So Ivan, do you know anything?
So I think maybe the comment is referring to another botnet that Microsoft is taking down, which is called the TrickBot. So as I said, with peer-to-peer botnet, it's not like it's difficult to say like I've eradicated 100% the botnet. Sometimes like a fight, and a success is like reducing by 2/3 the size of the botnet. Also, another thing that we should actually think about it very carefully. Let's say that we dismantled TrickBot, Necros, any bot we can think of. We need to think about the people behind their expertise, their skills. That is not going away. They probably will be back with another solution. So again, it's a fight back and forth and a constant struggle.
Excellent. So there was another question here in the question section about a resurgence of P2P botnets in the past 10 years. Do you think that that has anything to do with any particular factor?
Yeah, sometimes difficult really to understand why some techniques actually have the best moment in the past and then they come back later. Also, because one idea is that the attack surface, the targeting is evolved over time. So something which were available and did work, let's say, best, and essentially meant at the time that peer-to-peer botnets were going to fade away. Now that condition is restored. So this is what, let's say, it's sometimes complicated. Also, it might even be that the organization with a specific skill set to pull off a specific operation got some time to do that. So yeah, it's always pretty complicated to answer this absolute question, if I may.
Yes, absolutely. And so we are getting a little bit low on time here, unfortunately. So let's move on to some of our further reading slide, if we could. And some additional resources on our last slide. There we go. Yep. There we are. Thank you. So do you guys have any closing comments before we summarize with our follow-up resources?
I think we covered everything that we wanted, so I'm happy with that.
Stay safe.
Yes, very valuable information. Yeah, thanks for sharing it. So if anyone needs any more information on this particular topic, we have a few resources online on our website. You can go to our blogs page and you can find overcoming the challenges of detecting P2P botnets on your network. We also have a web page for our labs team with all kinds of great threat advisories, CVEs, some community tools that we offer. We also have a community edition of Guardian that you could leverage to check out your environment and the product. We also have some interesting threat research reports, some MITRE attack framework blogs, and some more webinars around the MITRE attack framework, and a data sheet on threat intelligence that you can find all the links on this last slide in this webinar, but they all are available on our website. It should be pretty easy to navigate to. So thank you very much for attending today. And as always, stay safe, stay secure, and thanks again for everything that you provided today, Ivan and Giannis. I hope that the community got a lot of value out of what you guys provided today.
Thank you, Chris.
All right, thank you.
Bye, everyone.